Okay. Thanks. All right, good. So a couple things you'll notice. One is that I'm not Dan. Although I'm also from the East Coast, are you from the East Coast? Must be. Got to be. Although I'm also from the East Coast, I don't speak quite as fast as Dan does, although, we'll see. And I haven't quite figured out the whole video thing, so maybe I'll work on that. But, hopefully we'll keep the momentum of the class going. Dan's been doing a great job on all the hard stuff at the beginning of the semester. So, okay. So, in addition to a shift of who's standing up here, we're about to shift topics a little bit. And so what we're going to do now is talk a little bit more about what was the original title of this class, which is machine structures. And we're going to focus on memory. So I also looked around in the news to see what's going on. And I don't know if you noticed, but there's a group in Switzerland that believes that they've been sending particles to a lab in Italy faster than the speed of light, which, as you guys know, that's not supposed to be possible. So given that we're thinking about performance of computing systems in this class, I wanted to think a little bit about how the speed of light impacts computers. And this is a really interesting article. This stuff is totally true. People that sell large amounts of stocks and exchange large amounts of currency, they do that in a very competitive environment, and they race with each other over who can get a deal first. And so this was a study basically saying, if you were looking for an opportunity between two markets where you could buy something, where you could buy something cheap in one market and sell it for more in the next market, and you wanted to do that lightning fast, then what you want to do is you want to find the place that's exactly in the middle of those two markets according to the speed of light. And so this paper talks about, for different markets, where those positions are, and if what these guys say is true, what's going to happen is there's going to be data centers built on islands and tops of mountains and out in the middle of the ocean, this stuff really happens. So I want you to keep this in mind when we're talking about performance of computer systems. Performance matters to a lot of people. All right, so here's what we're going to do. I'm going to reset the context in terms of the great ideas, talk very briefly about computer performance, and then we'll bring that up again later in the semester. Memory hierarchies, why they work, which is locality, and then we're going to talk about a particular part of the hierarchy called the cache. Okay, so remember our 6 great ideas? We just spent a bunch of time kind of mostly on the first one, right? Talking about the different layers of representation between your brain and then C and then assembler code and then machine code. What we're going to do now is Moore's law is kind of always there. We'll talk about that later. But we're going to jump down to number 3 here, which is the principle of locality, okay, in memory hierarchies. Okay, so first part is I want to say a little bit about computer performance. So what does it mean to say you've got two systems and X and Y, and X is faster than Y? So let's do a little thought experiment. So these were Randy Katz's original slides. So this is the car that he likes. Nice Ferrari. It carries 2 people if you're lucky. Also if you're lucky and it's running, it goes 11 seconds in a quarter mile. So call that 10 seconds. All right, so we're going to have a race here. Okay, here's our second contender. A school bus. Okay, holds 54 passengers, and I don't know how fast it goes. It actually doesn't matter. So let's assume it takes a minute to do that quarter mile. Okay, so now the question to you guys is, which of these is faster? Okay, which is the faster vehicle? And if there was an obvious answer, I wouldn't have shown it to you, right? So, and by the way, Randy does have, he had this, this is a funny little video. It takes 20 seconds. It's a bus going really fast. You might want to look at it. I didn't think it was worth taking time, but I left the link in there. Okay, so, if your idea of performance is what we call either response time or latency, that is, how long does it take to do something, then, the Ferrari is pretty fast, right? So, if the question is how fast can I go how fast can I do a quarter mile? Well, clearly the Ferrari is, 6 times faster, let's say, than the school bus. Okay, so, if you're thinking of buying that Ferrari, it seems like a good idea. All right, but if your metric is not response time or latency, there's other things we care about. What's called throughput or bandwidth, right? How much work can you get done in a given amount of time? Okay, so what you might actually be concerned about isn't how fast can a single car get, from the start line to the finish line. But what you might want to do is move a certain number of people from the start line to the finish line. And the question is, how long does that take? And what you'll notice here is, in terms of throughput or bandwidth, the school bus is much faster than the Ferrari, right? So it's 26, it's about 4 times faster than the Ferrari, okay, in terms of throughput and bandwidth. So, if you're concerned about throughput, you should buy the school bus, okay? And if you're concerned about response time or getting a date or something like that, you should buy the Ferrari. Okay, so the reason I point this out is because when we're looking at computer performance, we've got to be very specific about which one of these we're talking about. And sometimes the system with the better latency also has the better throughput, but that's not always true. And this is an example where those things are different. Okay, so keep that in mind. We're going to have a couple lectures on, details of computer performance later on in the semester. I just wanted to make sure you see this so you're thinking along the right way. All right? Okay. Why does this matter? Well, I already showed you one example. If you're in a competitive environment and you have to make decisions faster than the next guy, you want to be faster. This is another interesting thing. This is from a paper that the guys at Microsoft Bing wrote. And basically what they did is they measured, as their servers get slower, how much less happy do their customers get, and how much less money do they spend, okay? So if you're running an online service, there's a point after which, if your service is too slow, people stop using it. Or if they use it in a much different way, and then they're not as engaged. So even people that are building, sort of big web services, right, where the individual requests, look up a simple search term, bring up my Facebook page, whatever, they work really hard to make those things happen both with low latency, because you want it to happen fast, and also with high throughput, because you want hundreds of millions of people to be able to do it. Okay? And it matters. And it matters, to the business, and it also matters to how good and useful the system you're building turns out to be. So we've spent a lot of time in the previous lectures talking about, I've got some task I'm trying to do. How do I correctly translate it from my specification down into something that's going to run on the computer? Okay? That's obviously really important, because if you don't do that correctly, you're going to get the wrong answer. But you can't do that without thinking about performance. And that's why we worried about registers, and that's why we worried about, what was in memory and where it was. Okay? So now we're going to not worry about correctness. We're going to assume that's being taken care of by other parts of the system. We're going to focus completely on performance right now. Okay, so this is the simplest picture of a computer we're going to show you in this class. We'll show more detail later. But, you've got your input and output. You've got your processor over here. And sitting in between that is a bunch of memory. Okay, and as we talked about in the first class, that memory isn't just a unified, single level, but it's actually going to be made up of a bunch of different levels of that have different properties. And so, here are some example levels, and on sort of the Ferrari side, where things are fast and small, you've got your cache, and then it go to main memory, and then, you get out to the school bus side, where things are slower but a lot bigger, okay? And each of those has a role in the system, and that's what we're going to talk about. Okay, so we're going to focus today, and actually for the next couple of classes, just on kind of mostly 2 levels. So if you remember, we spent a bunch of time when we were learning about the MIPS worrying about what was in our registers and what wasn't, and moving things from memory into the registers so we could work on them, and then moving things from the registers back to memory so that we could use those registers again. Okay? The reason is we didn't have that many registers, right? If we could have fit the entire data set in the registers, we wouldn't have had to talk about any of that stuff. Okay? So, if you think about registers as sort of the top level of your memory hierarchy, you basically have, in a MIPS architecture, about 100 bytes, right? 128 bytes. You have 32 4-byte registers. Is that right? Or do you have more? A kilobit of registers. Oh, kilobit. So about 128 bytes, something like that. Okay? So that's what you got. All right? And what's great about registers is, first of all, the processor can access them directly, but secondly, they're really fast, so sub-nanosecond, right? When you can't fit things in registers, right, what did we talk about? We talked about loading words and storing words, right? So moving things between memory and registers. Memory is very different. You measure memory in gigabytes or more, okay? And the access time is several orders of magnitude worse. So instead of sub-nanosecond, it's 50 to 100 nanoseconds. Okay, so much, much, much slower. And so basically, every time you have to go to memory, and we've talked about this in different analogies, you're burning hundreds of clock cycles. So, time that you should be doing instruction processing where you're waiting for that slow memory to respond to you. Okay? So there's a fundamental problem there. There's a fundamental mismatch. All right. Why is this happening? Well, it's interesting. When we used to teach this class way back in the day, we used to have a graph that basically, oh, sorry, let me build that out. We have, the speed of memory here over time, and we have the speed of processors here over time. And, 5 years ago, we would show this picture, and they would just be diverging forever, right? Processors just getting faster and faster and faster. Memory, getting faster, but at a much more gradual rate. Okay? What's happened, as you guys are probably aware, and if you're not, you're going to be more aware, through the rest of the class, this speed up of processors has started to tail off. Okay? And so now what's happening is, instead of turning up the clock rate on our individual processors, we're just having more processors of a particular speed on a single chip. Okay? So this story is changing, but there's still a huge gap between processor and memory, and that's not going to change. So we've got a long way to go from sub-nanoseconds to 100 nanoseconds. Okay, so even if processors never get any faster, we're going to be dealing with this problem. Okay, but it's interesting that something that for 30 years was just a law of nature has changed, and that is going to impact the way we think about designing our software. We'll talk about that. All right, but for as far as we're concerned, this gap is, this gap is just growing, okay, and it's huge. Okay, so we've talked about memory hierarchies in the first class, but of course, that was a long time ago. So let's revisit that. Basically, at the top of the hierarchy, you've got things that are small and fast. As you move down that hierarchy, things get slower and bigger. Okay, and the reason that is purely economics. If you could afford more fast memory, you'd buy more. Okay, so in order to build a system that's affordable, you can't always have a Ferrari, right? You actually need, just to make for economy's sake, to have these bigger, slower devices. All right, and so the kinds of systems we're talking about, basically. At the top we have registers. I'll show a picture in a second, of course. And then, this goes all the way down to, say, disks. Okay? And I guess the question up here, which is an interesting question, is, are there systems where that bottom, that slowest, biggest level of memory is even bigger and slower than a magnetic disk? So is anyone familiar with any technologies that might even be below disk in the hierarchy? Yeah, so tape is the classic one, right? So believe it or not, a lot of large computer systems still have a level of tape. And in fact, if you go up the hill here to Lawrence Berkeley Lab, they run one of the hugest tape farms there is anywhere. And they actually have room. The tape devices are really amazing things. They have robotic arms that go around and find the right tape for you. And the first thing they do when you do an access is they look around to make sure nobody's standing in there, because otherwise they'd smack them on the head and something bad would happen. So those are really, really slow devices, but they have tremendously high capacity. All right, but we're not going to worry about that. In this class, we'll go maybe down to the disk and no further. All right, so here's that picture. This is turned on its side, but the processor's over here. We've got our registers, and then we go through the memory hierarchy. So we have an instruction. We have an instruction cache and a data cache. We have kind of first level. These TLBs we'll talk about later. Those are translation buffers. We have instruction and data cache. that are actually, in the processors. They're on the same chip. Okay, and then we have other levels of cache that are, maybe on the chip, maybe on the same board as the chip. And then, we go to and then we go to main memory, which is probably on another board that's near the processor board. And then, then we go out to the disk, which is somewhere else. Okay, and again, as you're heading away from the processor, speed is getting worse by orders of magnitude, and size is getting better, also by orders of magnitude. Okay, that's the fundamental, that's the tension we have in trying to use this thing. All right, and it seems really complicated, right? And it is. And so if we didn't need it, if we could figure out a way to avoid levels of the hierarchy, we would. Yeah, question.
So does speed depend on physical distance from the processor?
Speed does depend on physical distance from the processor, and it also depends on the technology that you use to actually make the transistors that are storing the information. So, SRAM is made out of a certain technology that's faster. And I don't know, are we going to talk about that? I think when we get to sort of transistor level design, we'll talk about this kind of stuff. But SRAM is made out of transistors that are much faster than DRAM, but they're also much more expensive. Okay? And the stuff that's near, the real estate that's near the processor is incredibly valuable because, especially if it's on the chip, you could either use it for more processors or for memory, and so you have to make that decision. So it's a combination of, the underlying technology and, how far it is. Yeah? Mm-hmm. Yeah, so the question is, when I read about processors, I read about different L caches. What's L? And L is exactly this. So L stands for level. And basically what you have is, I'm showing two levels. So that's level 1 cache, and that's on the chip. In this particular picture, level 2 cache is on the board, but not on the chip. Okay? In a lot of processors today, you have level 1 on the chip, level 2 on the chip, and maybe even more. Okay? And then everything after that is off chip. So level is L, the L in the cache, when you see that when you're buying a processor, is exactly what we're talking about. It's what level of the hierarchy are you at. So registers are 0, and then level 1, level 2, and so on. So thank you for, that makes it clearer to everyone, I bet. Yeah, please.
So there could be more than 2 levels of the level?
Yeah, absolutely. There can be multiple levels of cache. There can be multiple levels even of memory. You can have memory that's on the motherboard. You can have memory that's on a different board. You can have memory that's on a different server that you can use from your server. So yeah, you can just build this out to as many levels as economically makes sense. Yeah. And this is, people spend a lot of time on this stuff because it's really what makes the difference between a really fast system for an affordable price and one that's not as good. And if it's not as good, people aren't going to buy it. Okay, any other questions on this? Because this really is fundamental. This is what we're talking about. Okay, and this is given to us by the laws of nature and economics. It's not really our choice. Yeah, in the back. So that's an awesome question. So if we store a word, if we do store word in MIPS, first of all, what happens, which wasn't exactly what you asked, but the second question is, then can we tell it what should happen? You'll notice when you were writing MIPS, you didn't think about caches at all. Okay, you thought about register and memory. Okay, but if you look at this picture, my register's over here, my memory's way over here. Okay? So it's actually the hardware that's doing the translation for you. So the hardware is going to manage, I'll talk about this in a second, the hardware is going to manage that whole caching process. So it's invisible to you as a programmer, and it's invisible to you as a compiler writer. Okay? Now, can you in MIPS, and I'm going to defer to Dan here, can you in MIPS sort of say, hey, don't write, to the memory, write it someplace else? I don't believe so, right? So in MIPS, it's a very simple model. You've got registers, you've got memory. Okay, and then you've got I/O, I guess, that we didn't really talk about. Okay, because that's going to be hidden by the operating system. Okay, so this is interesting, and this is also a key point that I want to make today. A bunch of this stuff is hidden from you, even when you're thinking in sort of bits and bytes at the MIPS level. You still don't have control over this stuff. Okay? Yeah, go ahead.
Still have memory accesses. If you know what the size of everything is, you can guarantee that that's going to be in there.
Very good. So Dan, who is either a very good student or what's your name, Dan? Okay, so Dan pointed out to me that, and he's quite right, that you as a programmer, if you know the architecture, you can be clever about things and get the cache to perform better than if you didn't know what was going on. So you'll see how the cache works in a second, but if you know how big the cache is, you can write your program accordingly and avoid a lot of performance problems. Good point. Great. All right. Anything else about this stuff? Okay. So the Ferrari bus thing you got, this takes a little more. That's okay. This is a little more abstract. Okay. Good. So, here we are again, memory hierarchy. And the only reason I'm showing this slide again is because I wanted to make a point. So, as you go down this thing, things get slower. As you go down, things get bigger, right? We keep talking about that. One thing I'll point out is this clever abbreviation for cache, which is a $sign. So L1 cache, L2 cache, just like we were talking about. But the other thing that's important is how do these levels talk to each other? Okay. So what you see is, as you know this, from the processor, when you're going between the processor and something below, right? So when you're going from a register to your abstract view of what memory is, you basically write words, right? So you write out registers and you read in registers. So you're dealing with 4 or 8 byte chunks, all right, depending on 32-bit or 64-bit architecture. Okay? Typically, as you go down this hierarchy, that transfer unit gets bigger and bigger. So as an example, when you go from level 1 to level 2, maybe instead of 4 to 8 bytes, you're doing 8 to 32. So you're reading in bigger chunks. Okay? When you go from L2 to main memory, you're going to read, 4 of these things. So maybe 4 times 32 bytes, 1 to 4 of them. Okay? When you go from main memory to disk, you're going to read big disk blocks. Okay, so maybe you're going to read, 4K bytes at a time, or maybe 16K bytes at a time. Okay? So as you go down this hierarchy, you're getting bigger and bigger chunks. Okay? And the reason is that every time you cross this boundary, it's expensive. So you want to minimize how many times you have to go from a higher level to a lower level and back. Okay? So the more you bring in from the lower level, to an extent, the fewer times you're going to have to go down there. But you have to be smart about it. Okay? So enough said. All right? So what you'll see is, what's interesting, and that's what all this text here says, is so the way it works is you've got, let's say, so secondary memory is disk, and let's say that's as far as we go. So the amount of data in our universe is whatever's on the disk. Okay? When we need stuff, we check, is it in the register? No, we bring it in. Is it in the L1 cache? If it is, we use it. If it's not, we bring it in from L2. Is it in the L2 cache? Same question. If it's in there, we use it. If it's not, we bring it in. Main memory, same thing. All right? And if it's not in main memory and we need it, we get it from the disk. Okay? And then if we go down the disk and it's not there, we get an error, right? Because the disk is all we got. So what that ends up doing is data ends up living at multiple places in the hierarchy, right? So the stuff that you're using gets brought in. Not everything is out on disk, but, data that's useful gets brought in from disk into main memory, from memory into L2, from L2 into L1, from L1 into the register. And that stuff in the register is likely there's a copy of it in every part of the hierarchy. So, wow, a couple questions. So I think I saw your hand first. Okay, so cloud computing we're going to talk about in detail. But cloud computing, in terms of having multiple machines, the memory of another machine is much further away than your own memory. And there's an interesting question of whether the memory of another machine is further away than your local disk. That's an interesting question. And it depends how you set things up. But we'll talk about that. But if you remember the analogy I gave you at the beginning of the semester about going to disk is like going to Pluto, going to the next server is like going to Andromeda. Okay, it's far, far, far away. You don't want to do it if you don't have to. Yeah? How do you clear cache? I'll show you how to clear cache in a couple slides. Okay. Any? I saw. Wow. Okay. Yep. Yep. Yeah. So there's a question that says, so let me paraphrase your question. If I read a big chunk from a lower level, it's going to take me longer to read it, and isn't that a problem? And the answer is yes. And you're in good shape for the peer questions if we ever get there. I saw some hands here. Yeah.
So when the person changes stuff into the data and the register, then does it have to store it all the way back down?
Also a very nice question. So if the processor changes something in the register, does it have to store what was in that register? Let's say that thing originally lived on the disk. Does the processor have to store everything back out to the disk? And the answer is no. You have to store it to memory, right? Remember last class we talked about what you have to save, what's going to be preserved, what isn't. If you care about it, you have to put it in memory. The hardware is going to make sure it goes through these caches to memory, but the operating system is going to make sure it goes from memory to disk. You don't have to worry about that as a programmer. That's an operating system thing. And we'll talk about that later in the semester. Yeah? Okay, so the question is, are we going to talk about why certain types of memory are faster than others? And the answer is no, we're not really going to talk about that in class in terms of like the underlying, silicon. But there is some discussion of it in the book, and we definitely have classes that talk about that stuff, which we can point you to. But we're not going to cover it in this class. Okay, I think you had your hand up for a while. Yeah?
Where exactly does the stack pointer?
The stack pointer, so here's the beautiful part of this lecture, or this topic, is it actually doesn't change anything from what Dan told you about. So the fact that there's 1 or 2 or 3 levels of cache in between your processor and the memory, that gets hidden, the hardware is going to hide all that from you. Okay, you don't have to worry about it. It's going to manage that. So everything that you learned about in the last class is still valid. You don't have to, memory is memory, registers are registers, and that stuff in the middle is just going to make the memory look a lot faster than it really is. Okay? I think there's one more question, then I want to move on. Yeah?
What chunk of memory gets moved from the secondary memory to main memory and then everything? What chunk?
Okay, so we're going to talk about that kind of thing right now. Okay, so the question was, what gets moved? How do you decide which data gets moved up and down this hierarchy? We'll talk about that right now. Okay? All right, good. This stuff is fundamental, and, if you're going to take my database class, it's great if you already understand this before you come in, because this is the key to making, databases run fast. It's the key to making everything run fast. Okay, so I think we've probably talked about this a lot now, but let me just make sure I hit it. This idea of a cache, again with our cute little abbreviation of a $, it's there to hide the fact that the memory is so much slower than the processor. Okay, that's all it's there for. It's just for pure performance. The hardware is going to handle it, so you don't have to worry about it as a programmer. Actually, I already talked about this. The cache is a copy of it's a copy of a small piece of what's in main memory, right? Because the cache is smaller. The size of the cache is a lot smaller than the size of memory. And modern processors, if you guys have already figured out, have a bunch of different levels of caches. And in fact, as I already told you, there'll be a separate cache for the instructions and a separate cache for data. And we'll talk about why that is in a second. Okay? So that's this idea of caching. So why does it work? Okay, so we've added in all this complexity, right? We're playing this weird game where we've got a terabyte of disk, let's say, right? So 1 billion gigabytes. Is that right? Or am I off? 1,000 gigabytes? 1,000 gigabytes. Sorry. I was just talking to my friends who do petabytes, which is what 1 billion gigabytes is. But okay, we'll just do a measly terabyte. So 1,000 gigabytes of disk. You've got 128 bytes of register, right? So think about that ratio. How many orders of magnitude is that? And then everything in between, okay? So how could that possibly work? How could you possibly front a terabyte of data with 128 bytes? It just doesn't even seem possible, right? So, well, why does it work? Okay, well, the miracle is this thing called the principle of locality, which is at any given time, a program tends to access only a very small part of that memory. Okay, so yes, you have a terabyte, but if you're writing MIPS code, you're writing programs that really only access, the registers and a little bit of memory. Okay, so we're gonna leverage that, right? So that we're only gonna keep the stuff that we need close to us. And yeah, that's going to change over time as the program kind of moves on. It's going to need different things, but then we'll bring that up and we'll keep that near us. Okay, so that's why it's going to work. So in the book, there's this wonderful library analogy. By the way, as I was reading this, I was like, how many of you guys have ever gone to the Doe Library and studied? How many people have actually studied in the library? Oh, not bad. Okay. How many of you guys have ever actually used a book that was in the library? Oh, okay, I feel better about my tax dollars now, a little bit. Okay, but so you know what I'm talking about. Okay, so let's say you had to write a book on some, famous author. Let's pick J.D. Salinger, and you're sitting at the library. You've got your little desk, so you go to the stacks, you get your books, you can put them on your desk. Okay. If you're doing your report, you realize, there's another book I need about J.D. Salinger. You can go back to the stacks and get it, and you can bring it and you can put it on your desk, okay? Except, what happens if you run out of room on your desk, okay? Well, then you're going to have to decide what that's on your desk you don't need anymore, or what do you need? What of all the things you have on the desk, what's the thing you're least likely to need next, okay? And then if you're a good person, well, actually, you just put it on the rack and they're going to restack it for you. If you're a bad person, you put it in your backpack or something. But, but that's it. You've got this massive, massive library, and our library is truly massive. And you've got this small desk, and it's exactly the same thing. You're the processor, okay? And so you've got, 10 books, and somehow that, that percentage of a percentage of a percentage of percentage of all the books that the UC Library has, hopefully those are the ones you need, okay? And if they're not, then you got to go get the other ones and put some others back, okay? So that's the analogy. That's what the processor's doing, right? The registers are its desk. Disk is the library, and, we're going to manage all that stuff going back and forth. Okay, so why does this work? It works because of locality, right? Because the amount of data you need, when you're writing your report about J.D. Salinger, you probably don't need the books on, the history of, I don't know, boy, I'm out of examples. Anything that doesn't have to do with J.D. Salinger, right? So that's why it works. So let's talk a little more about that idea of locality. And it turns out that there's two types of locality that we're going to use. Okay, and this is important, right? This is one of the things, if you look in the book, this is one of the things that they actually have in the margin, right? Because it's important. Okay, so temporal locality, right? Locality based on time. That says if I use an item, so let's say I've got a byte of memory. If I use a byte of memory, chances are I'm going to use it again. Okay? So if I just used it, I'm likely going to use it again. So, what's the weather going to be like tomorrow? It's probably going to be like it was today, right? That's in the absence of any other information, that's your best bet. Okay? So what am I likely to use next? Well, it's probably what I just used. Okay? So that's temporal locality. Spatial locality is kind of a little more subtle. It says the things I'm going to use are probably near physically the things that I just used, okay? So temporal locality, I've got my 10 books about J.D. Salinger. I just looked at one. I went to another one. Oh, I got to go back to the first one, okay? So that's kind of temporal locality. Spatial locality says, hey, I'm looking for a book on J.D. Salinger. When I get to the stacks, actually all the books there are about J.D. Salinger, right? So there are other books nearby the one that I wanted that also might be useful. That's spatial locality. Okay? And both of those are important, and they're both different. We treat them differently. Okay? But that's how, that's why this narrow hierarchy, right, this 128 bytes sitting on top of a terabyte, that's why that's going to work. Okay? Because I tend to use things either that I just recently used or that are near things that I recently used. Okay? That's locality. Yeah?
So when we're doing memory stuff, do we have to think about this spatial locality, or should we just let it?
Oh, okay, great question. So when we're doing things with memory, do I have to worry about this? And the answer is absolutely. So the trick to making things go fast, and this is one of the things that Dan was talking about earlier, is to know, yes, you want to arrange things so that if you're using some data, you try to use it as much and then move on to the next thing rather than keep hopping back and forth, right? You can change that in your program, right? You want to organize your memory so that if you use this thing, the thing you're going to need next is right there, right? Yeah, as a programmer, you definitely want to worry about both of these. Yeah?
So in terms of spatial locality, it's better to use things like arrays that are stored like all
You're jumping ahead of me, but absolutely. Arrays are a great structure, especially if you're going to scan them, right? That's exactly spatial locality, okay? Because that's why I put them all near each other in memory, okay? All right. So, in fact, I think that's my next question, is why does this work? Okay, well, what things about the way you write your program contributes to temporal locality, okay, and spatial locality? So, temporal locality is pretty easy, right, for code, right? I do this instruction, then I do this instruction, then I do this instruction, then I do this instruction, right? So that's, the instructions I tend to access tend to be near each other, except when? When I do a jump, right? Remember all those jump routines? Oh, that sends me someplace that's further away. That's going to cause us some problems for performance, okay? What about temporal locality? When in a program might you find some good temporal locality? Any ideas? Yeah, iterations, when you're in a loop. So, I equals I plus 1, do something, I equals I plus 1, do something, right? You're just, zipping around in this little piece of code. That's going to be good temporal locality. And to your question, that's the kind of stuff you worry about when you're writing code to make it go fast. And in data, as we already talked about, there are certain data structures that have better locality than others. So, if you know that you're scanning through a bunch of data, chances are an array is going to give you better better spatial locality than a linked list that you sort of allocate piece by piece and is spread all over memory. Okay? So you got to worry about stuff like that too. All right. So Dan's looking at his watch saying there's no way he's going to get through this, and you're probably right. But that's okay. This is it's my first try. I'll do better next time. So, okay. I'll let you out on time. Don't worry. Keep your hands out for next time. Okay. All right. So who has to worry about the management of this stuff? All right. Registers to memory, you already know that, right? If you're writing assembly code, you write, load word, store word. You're moving stuff from memory, into registers back and forth. Okay? If you're using a compiler, the compiler is going to do that for you, right? You don't worry about registers at all. You think everything's in memory. Okay? That's nice. Okay. Cache to main memory. Okay? You don't have to worry about it. The hardware is going to do that for you. That's why when you write MIPS code, you never see anything about a cache, right? You got registers, you got memory. There's a big void in between. In fact, before this lecture, you might not have known there was anything in between. That's because the hardware is handling that for you. Good thing for us. It's an abstraction. Thank you. Abstraction. Yes, that's an abstraction. And main memory to disks, it's the operating system's problem. We'll talk about that later. Okay? So we're just going to focus on this one. All right. Oh, boy. Okay. So we're going to worry about how do you do the management between the cache, which is small, but not as small as the registers, and the main memory, which is bigger than the cache. Okay. So now we have to do our design questions. Okay. So let's see. What are they? And this is a little different than what's on your handout. So just keep a note of that. The slides that I'm presenting will be posted on the web page, so those will be the ones of record. But how best to organize memory blocks in the cache, right? So we've got some amount of space in the cache. How do we organize it? When I take something from memory and put it in the cache, where do I put it? That's to which block of the cache does a given main memory address go map. That's called a map. How do we know which blocks of main memory currently have a copy in the cache? So how do I know what's in the cache? That's question 3. And how do we find the stuff that's in the cache quickly? So if I'm looking for a particular memory address, how do I quickly find out whether it's in the cache or not? Okay? So just again, how do I organize my cache in terms of blocks, right? In terms of chunks of cache memory. How do I decide where in the cache to put a block? How do I know which blocks from my memory are actually in the cache at a given time? Because remember, cache is a lot smaller than memory, so I can't put them all in there. I got to have a subset. And then how do I find, if I'm looking for something, how do I find quickly whether it's in the cache or not? Okay? That's what we're going to design. Okay, So today we're going to talk about sort of the simplest way of doing this. It's called a direct mapped cache, okay? And basically, so we have blocks in memory. We have a much smaller number of blocks in the cache, and we're going to move things from memory into the cache, and then if they get updated, we're going to move them back out, okay? So basically, each block of that memory in a direct map cache can end up in exactly one place in the cache, okay? So, you have some particular byte that you want to get at. You look to see if it's in the cache. If it's in there, great. If it's not, you have to go out to memory and get it, and there's only one place you're going to be allowed to put it in the cache. Why is that? Because then it's going to be really easy to find, okay? So that's what a direct map cache does. So basically the way it works is you have an address in memory, and you take the modulo of that, right? Remember the modulo? And if modulo of a power of 2, you just take that many bits off the bottom. Okay? So the block address modulo the number of blocks in the cache, that's going to tell you where, given an address, where in the cache that address belongs. Okay? The tag is another piece of the address, which is going to tell you, hey, what's actually in that block? Is it what I'm looking for or not? Okay? And it sounds complicated, but it's actually not too bad. All right. So before I show you a picture of that, let me just give you a little more terminology. So a request comes in, right? There's a request in the processor. Let's say you want to load a word. You got to get that word from memory, okay? So you say load word. The hardware says, oh, okay, well, memory is really, really slow, so I don't want to get it directly from memory. What I want to do is I want to look in my cache to see if it's there, okay? And if it is, I'll return it from the cache. If it's not, yeah, then I got to go to memory and get it, okay? So when you look in the cache for a piece of data based on its address, if it's in there, that's called a hit, okay? So that's a cache hit. If it's not in there, it's called a cache miss, okay? So you go to the cache and you say, hey, I'm looking for the data that's at this address. Do you have it or not? If it has it, it says yes, returns right away. That's a hit. If it doesn't have it, some magic happens. That's called a cache miss. Eventually, you bring it into the cache, and then it gets returned. Okay, that's called a cache miss. And the question is, on a cache miss, you have to go out to memory to get the data. Okay? And when you bring it into that direct map cache, there's only one place you're allowed to put it. And the question is, was there already something there or not? Okay? So you're getting your piece of data from memory. You got to put it in this one place in the cache. It's quite possible that there's already something else in that spot. Okay? If there isn't, you're great. You just put it in there. If there is, then you got to replace what's in there. Okay? And if what's in there is dirty, you got to write it back out. If it's been updated, you got to write it back out so you don't lose it, and so on. Okay? Again, this is all happening by the hardware. So you go, you ask the cache, do you have this piece of data I'm looking for? If it does, that's a hit. If it doesn't, there's a miss, and then it goes through some trouble to get you that stuff. Okay? So, okay, good. So now we can see how this direct map cache works. Okay, so here's our memory. It's a huge memory of, I don't know, however many. So each, sorry, I can't, I'm going to get dizzy if I look up there. Each block of our memory is a word, so that's 32 bits, 4 bytes. Okay, and we have this many of them. And then this is our cache, which, as you can see, is much smaller. But of course, it's going to be much faster. So we have 4 entries in our cache. Okay, so what we could do is we could take our address, right? These are memory addresses. Okay, 00000 is the first one. 001. Okay, these are, sorry. 00, this one is 4 bytes. So that's got 0001, I'm sorry, it's got byte 0, byte 1, byte 2, byte 3, and then byte 4, byte 5, byte 6, byte 7, and so on, right? So we're going at this thing in 4 byte chunks. All right, so the question is, for a given memory block, for a given word in this case, where in the cache should it be? Okay, and that gets determined by these middle 2 bits here. Okay, so basically, since my block size is 4 bytes, I need 2 bits to represent that. So I ignore the lower order 2 bits. Okay, the next bits I'm going to use to determine where in the cache I should go. And so I have 4 lines in my cache, 4 blocks. So that means I need 2 bits to talk about that. So the first 2 bits are the byte in the word. The next set of 2 bits is where it would go in the cache. So if I look at those first 4 words in memory, they would go, if I read them into the cache, this top one will end up here, the second one will end up here, the third one will end up here, and the fourth one will end up here. All right, and they're color-coded. Okay? So that's great. And if my cache was the same size as memory, I'd be all done. But it's not. So what happens if I read one of the next 4? Well, those are going to have to go into those same locations, right? And you can see this is all based on those middle 2 bits. Okay, likewise, the next 4 go into those locations. And here. So in this case, our memory is 4 times the size of the cache. So basically, each piece of memory, each word in memory, is going to have to share its cache line with 3 others, right? So you're going to have 4, the ratio of memory to cache is 4 to 1. And so any cache line could hold, any cache block, could hold any one of 4 different items. Okay? So that's direct map cache. And then the other question is, well, wait a minute, when I look at this cache, yeah, I've got data in there, but how do I know which of, like if I look at this cache block 00, yeah, there's something in there, but how do I know which of the 4 possible things it could be? That's the last part of the address. That's called the tag. And that's the high order bits, okay? And so the remainder of the address is used as a tag. So I write into the cache not only the data, right, which is, say, the value of whatever was in memory. I bring that whole word and put it in the cache. But then I also indicate the top 2 bits of the address so that when I look in there, okay, if I'm looking for a particular address, I look in the one place in the cache it could be, okay, and if there's something in there, I have a flag that says valid or not. If valid is set to 0, that means there's nothing in there. If valid is set to 1, it means there's something in there. But just because there's something in there doesn't mean it's what you're looking for, okay? So what I have to do is I have to look at the tag and I say, that tag in there, is that the same as the top 2 bits of my address? And if it is, that's a hit. And if it's not, it's a miss, okay? And on a cache miss, if there's something in there, you have to, get rid of, the hardware will take care of this, but it'll get rid of what's in the cache, it'll bring in the new thing. That's a cache miss with replacement. Okay? So what we're doing is we're taking that address and we're breaking it into 3 pieces. Okay? From the lowest, the smallest bits to the biggest ones. The offset, which is where in that block, which byte in that block am I interested in. The index, which tells me which line in that cache, which block in that cache I'm allowed to go into, and because it's direct map, there's only one. And then the rest of the address is this thing called the tag, which is all the rest of the bits. That's going to be put in the cache as well, so that when I go to see what's in there, I check to see, does the tag that's in the cache match the tag of the address I'm looking for? And again, that's all based just on the bits in the address. Okay? So this is cleverly called the TO. I think that Dan made that up. I don't know. Did you make that up? Slides I saw from earlier semesters said you did. So it's TO. That's how I remembered it when I was getting ready for this lecture. So, reading along, the tag is the highest order bits. That tells you that's the identifier inside the cache. The index is the middle bits. That tells you which block in the cache this thing is going to go into. And then the offset is within that block, which byte are you looking at? Okay, that's TO. Okay, and by looking at the number of bits that you have in each of these, that tells you about the structure of your memory. So if you have an n-bit offset, right, how many bytes do you have per block? Well, 2 to the n, right? So when we had blocks of size 4 bytes, we needed 2 bits for the offset. Okay? The index, again, if you have an n-bit index, that tells you if you have n-bit index, then you have 2 to the n entries in places in your cache, blocks in your cache. Okay? So if you wanted to have a cache of 1,024 lines, you would have 10 bits in your index. Okay? And then the rest of the bits go to the tag. Okay, so that's the summary of the TO. What I need to tell you next, and I'm breaking Dan's cardinal rule, and I'm sorry about that, but I'm going to have to use, there's about 4 or 5 slides left. I'm going to have to start with those next time, plus a little review. But the key points, let me jump ahead so that I just, you see, I'm giving it away. You should go through the slides when we put them online. That's where all the good animations are. Come on. Sorry. Let me just make sure I tell you what I told you, and then I'll let you out of here because it's a nice day out there. So, we spent a bunch of time talking about memory hierarchies, why they exist, okay, and how to make them work. And then this idea of a direct map cache, which is we've got way more stuff in memory than we can fit in our cache. So how do we do all the accounting to make that work? All right, so when I see you on Monday, we'll continue with this. All right, have a good weekend.